So the last things that we talked about on Wednesday concerned primarily with the valence bond theory. That is sigma bonds versus pi bonds and what the difference was between them. Remember, sigma bonds are the result of those head-on interactions of orbitals. So I have, let's say I have two orbitals like this. Their ability to interact with each other head-on and overlap without running into issues of repulsion between the two nuclei would result in a sigma bond. Whereas pi bonds come about as extra bonds where orbitals that maybe could not overlap on their own but orbitals like these, where I can't get them close enough together that they can overlap directly, because at that point the nuclei are just too close together. They're going to fly apart, they're going to repel. But if I have a sigma bond already present that's holding those two together, an additional bond like this, where they don't have to get as close to get direct overlap, but they kind of are close enough that they can associate with each other. That's what a pi bond is. Now, this kind of bonding, there's not enough interaction between these electron nodes and the nuclei to really do anything considerable. So you can't have a pi bond by itself. But if there's already that sigma bond present, the sigma bond creates enough attraction between the two nuclei that a pi bond can become possible as an additional bond. So where we see pi bonding taking place is in multiple bonding. I have a double bond. I have a triple bond. First bond between them, always sigma. But that second bond can be a pi bond. That third bond, if it's a triple bond, can be a pi bond also. So that's kind of where we're leaving off. And so if we start to explore this concept of hybridization, what hybridization tells us is a couple of things. First of all, hybridization tells us how we get to the molecular shape, to the domain geometry that we would expect based off of a steric number. So in reality, we are not doing anything different or in opposition to what we have been doing the past week or so. So in this first example, I have the molecule methane, CH4. If I were to draw the Lewis structure of methane, it would look something like this. Now, based on what we've taught you thus far, you would be able to look at this and say, okay, steric number here is 4 because I have 4 bonding groups and no non-bonding groups. 4 plus 0 is 4. 4 is my steric number. And then from there, you could go into, okay, well, at steric number 4, it's a tetrahedral. Tetrahedral bond angles are 109.5 degrees. And since this one has no lone pairs on it, it is going to stay as tetrahedral and 109.5 degrees. There's no distortion coming from those lone pairs changing the shape or changing the bond angles by compressing them. All that hybridization is doing is trying to explain how do we get from carbon in this state, where we have carbon in its atomic state, and that carbon is 1s2, 2s2, 2p2, just like we taught you in module 3, how to do electron configurations. How do I go from that orientation to an orientation that will allow 4 bonds to form? Because after all, if I'm looking at this strictly from an atomic standpoint, the s orbital is already filled. It's already paired up. Why would it do any bonding? It would have no reason to. The orbital's already full. Only those 2 unpaired p orbitals would have a chance at bonding. And we know from an orientation standpoint, those 90-degree angles don't do very well for sigma bonding. So again, the question becomes, how does it happen? What goes on? Well, what we have to start thinking about is the method here, it comes down to steric number. Steric number tells us, okay, I need 4 equivalent electronic positions. Now, to get those 4 electronic positions that are equivalent and equidistant from each other, I'm going to need to take what I have as far as atomic orbitals are concerned and reimagine them. That reimagination is what we call hybridization. And so we always start from the lowest energy orbital and work our way up based upon our needs. So in any hybridization model, we're automatically going to have the s orbital integrated, because the s orbital is the lowest energy orbital in the entire energy level. And so that one's getting thrown in automatically. Now it just becomes a matter of how many orbitals do I need to set up the electronic environment that I want. Here again is where steric number comes in. The steric number tells me, look, I got 4 regions here. So what does that mean? That means I need 4 hybrid orbitals to do it. Where do those hybrid orbitals come from? Well, they come from the valence sublevels, the s and the p. So I have the s. To get to 4, I would need all 3 of the p. And so we call that hybridization sp3. So I need 4 hybrid orbitals because my steric number is 4. And I'm going to pull from the s and all 3 of the p's to do it. This is called sp3 hybridization. Now, in that process of hybridization, now we come back to Hund's rule. Remember Hund's rule from module 3. I have a group of equivalent orbitals that has similar energy. I don't start pairing them up. I spread them out. So I have 4 hybrid orbitals, and I also have 4 electrons. Instead of pairing them up like they are in the atom, they now all get spread out. Those 4 electrons that are now spread out over those 4 hybrid orbitals, they're primed for bonding. Because a covalent bond is a sharing of electrons, right? So in an ideal sense, that means that we need to have 1 electron from the first atom being shared with 1 electron from the second atom to make that covalent bond. And as we've already talked about, that covalent bond has to be a sigma bond, has to be a result of that direct overlap. So now I have the capability to do that. I have carbon with 4 hybrid orbitals, each one with an electron in it, and I'm pairing it up with hydrogen, and each hydrogen has only 1 electron anyway. And so the 1 electron from the hydrogen pairs together with the 1 electron from the hybrid orbital, and there's my covalent bond. It's the marriage of the sp3 hybrid orbital from the carbon and the s orbital from the hydrogen. Why doesn't hydrogen hybridize? It has no way to. Remember, hydrogen's in the first energy level. It only has the s orbital. So there's nothing for it to hybridize with. So hybridization only takes place in atoms that are transforming into molecules where it's necessary to do that hybridization, to separate those multiple electrons from each other. Something like hydrogen with only one electron in total, there's no other electrons to separate from the pack. So I don't need to hybridize. Now, this kind of rationale does not only apply to circumstances where every single hybrid orbital goes and makes a sigma bond. Hybrid orbitals can be used not only for sigma bonding, they can also be used for electron storage. So take the case of ammonia here. In ammonia, I have this structure. And so if I'm evaluating steric number like I would have the other day, I would come to, again, 4 rebonding groups plus the one non-bonding group gives me 4 electron groups in total. So using what we know already, we know that this is a tetrahedral base shape. And so the difference between this and the methane is the fact that we've got that lone pair on there. These bond angles are going to be less than 109.5 degrees because that electron pair on the top there is going to push all of the other bond angles closer together. The actual shape here is trigonopyramidal because that lone pair of electrons isn't actually a bond. It's just empty space, basically. Repulsive empty space, but empty space nonetheless. The actual molecule is just the nitrogen on top and the hydrogens below in a pyramid shape. But the same kind of logic can still apply. Steric number of 4 means I need 4 hybrid orbitals. Those hybrid orbitals, we start with the s, we move on to the p. The p sublevel has a total of 3. 3p plus the 1s is 4 hybrid orbitals. sp3 hybridization is the mode of hybridization here. Now this time, what's different? Well, in nitrogen, I have 5 valence instead of 4. So these 5 electrons are going to move into the 4 hybrid orbitals, which means one of those orbitals is going to end up having a pair of electrons in it, which is exactly what we were predicting based on the structure and what we've talked about this past week. So nothing there has changed. Now we're talking about how does it go about happening? How do we still end up with a tetrahedral kind of base shape here for ammonia, even though it's not quite the same as our first example? Well, that's how. That pair of electrons there stays there. It's in a hybrid orbital. And so as being part of that hybrid orbital, it's still in a 109.5 degree space. It's still in that tetrahedral base shape. But because of its influence as a lone pair, because it has a greater repulsion, because it is unshared, those bond angles that are still in existence, they're going to shrink down. Now, the actual bond angle for ammonia is 107, but like I told you on Wednesday, we don't need to concern ourselves with that particular detail. We just need to understand that it's less than the 109.5 starting angle. So here's another picture of what went on in the methane and how we got to the 4 bonds there. Let's do a review question. Question is this: what is the hybridization state of nitrogen in ammonia? We just talked about it, so hopefully this is a pretty easy question to answer. I'll redraw ammonia here just in case we forgot what it looks like. All right, for questions like these, again, we go through the same process. Start with the steric number. Steric number here is 4. 3 bonding groups, 1 non-bonding set of electrons. 4 total. With a steric number of 4, I need 4 hybrid orbitals. So, easy way to do this, I can look at each of these. I can say, okay, if I tally together all the superscripts, which one gives me 4? sp3 would be the answer there. The other way, again, I could look at it logically. S is the lowest energy, P's after that, so that's 2. And so I need 2 more. P gives me a total of 3, so sp3 would give me a total of 4. Right. Any questions so far? All right, let's look at a different kind of question. What type of orbital overlap is responsible for this carbon to hydrogen single bond in this molecule? All right, with this one, so again, we know that the sigma bond is going to be between whatever the hybrid orbital is for carbon and whatever the hybrid orbital is for hydrogen. Only problem is hydrogen doesn't hybridize because it doesn't have anything to hybridize with. So we know hydrogen's contribution to this bond is going to be the s orbital that it has, which is the 1s. So automatically, just based off of that, I could eliminate A and B because hydrogen could not possibly hybridize. What's the steric number for this carbon? Show me. Give me fingers. Yeah. It's 3. Now, if you're thinking 4, remember, it's not the number of bonds, it's the number of bonding groups. So that oxygen is 1 bonding group, even though it has a double bond. So I've got 3 bonding groups, no non-bonding groups. My steric number here is going to be 3. Which means I'm dealing with a trigonal planar kind of geometry around that carbon. Now, 3 as a steric number means 3 hybrid orbitals. So I got my S, I've got my P, and how many P's can go in there to give me 3? I already have the 1S. I'm going to need 2 P's to give me a total of 3. So this is sp2 hybridization that's being described by that carbon. So I've got the s orbital from the hydrogen. I've got the sp2 hybridized orbital from the carbon. Those are the two things that are interacting. And so my answer here is going to be D. All right, so that example brought into for us a different kind of hybridization, sp2 hybridization, in fact. Now, the first kind of hybridization that we looked at was the hybridization where we had the S interacting with all 3 of the P orbitals. And the net result of that hybridization was this tetrahedral shape, the sp3. Everything's 109.5 degrees apart. And obviously that angle changes slightly if we start introducing lone pairs instead of bonds. But that was the orientation. That was what it looked like. Now, in sp2, what we see instead is, instead of having the S and all 3 P's, we're going to have the S and 2 of the P's. Now, when that happens, now we have only 3 orbitals that we need to hold far apart from each other. That's what gives us the trigonal planar shape. All 3 of those areas being 120 degrees apart, that gets them as far apart from each other as possible. The question is, what about this other orbital? What happens to it if it's not part of the hybridization? The hybridization tells us what makes sigma bonds, or what stores electrons. What happens to that p orbital that didn't get hybridized? Well, it's one of 2 things. Either it is left completely empty. Where do we see that? We see that with some of the exceptions to the octet rule where we don't quite hit the mark. So like boron trifluoride. Boron only has 6 electrons around it. From a formal charge standpoint, that makes sense for boron. But what does that also mean? Well, it's only got 3 bonds. That 4th orbital, it's empty. It just stays there. We see that for things like aluminum chloride. Aluminum chloride has a covalency to its structure, even though we think of it as being more ionic in nature. Same deal though. That's one direction. For those particular exceptions, it stays empty. The other thing that happens is that it is capable of pi bonding. So if I got an orbital that doesn't get hybridized, that is a potential pi bond if the circumstances dictate. So let's look at an example of that dictation. Here I've got ethene, CH2CH2. I can look at the bonding scheme here, and I can see that for this carbon here on the left, my steric number is equal to 3, and so I must be talking about an sp2 hybridization. For this carbon here on the right, my steric number is 3. I must be looking at an sp2 hybridization. Now, schematically, what does that look like for the carbon? Well, remember, carbon has 4 valence electrons. So those 4 electrons get spread out after hybridization. And go into the hybridized orbitals. They're going to be the ones that make sigma bonds. One of them goes into that unhybridized orbital to make the pi bond. Where are my sigma bonds? Well, I've got a sigma bond between the 2 carbons, and I've got a sigma bond between carbon and hydrogen, one on the top and one on the bottom. So there are my 3 sigma bonds. And obviously the carbon on the right here does the same thing. Sigma bond to the other carbon, sigma bond to each of the hydrogens. The remaining bond, that extra electron, that goes into the pi bond. And like we said, the pi bond is a little bit harder to form because you've got to get those 2 orbitals that are in parallel close enough to each other that the electrons can kind of commingle and interact. That doesn't happen because of repulsion unless that sigma bond is there first between the carbons. And so in the scheme, I've got 5 sigma bonds in total, and I've got this pi bond. All right, let's try to answer this question then. This time I'm looking at the carbon to oxygen bond. And in particular, I want to know about the sigma bond between the carbon and the oxygen. What kind of orbital overlap are we getting there? So since it's a sigma bond, we need to be thinking about hybrid orbitals. If we were asked about pi bonds, then we would know it's p to p. But we're being asked about sigma here, so we need to think about hybridization. So sketch it out for yourself here. What is the hybridization on the carbon? What is the hybridization on the oxygen? All right, so we've talked about carbon already. Steric number here has to be 3. This is the exact same example that we saw in the previous problem. So we're talking about sp2 hybridization on the carbon. So right away, you can eliminate a couple of these options based off of that. Now, what about the oxygen? What's the steric number on that oxygen? Yeah, it's 3, just like the other. So we didn't talk about shape with this particular kind of example of that steric number because, well, there really is no shape to it. It's linear because it's only connected to one atom. But as far as how are those orbitals interacting, well, they're in a trigonal planar orientation as well. Those two lone pairs are 120 degrees apart. They're 120 degrees apart from the carbon to oxygen sigma bond as well. So we've got sp2 on both accounts here. That's letter A. All right, any questions with hybridization so far? Okay, let's look at the third most common type of hybridization, sp hybridization. With sp hybridization, what we are seeing is the combination of just one of these p orbitals with the s, just one of them, which means we have two orbitals that are unhybridized. Now, just like we saw with sp2, that can go a couple of different ways. For compounds like beryllium and magnesium, which have been known to make covalent compounds, those two can be completely empty. Formal charge for beryllium and magnesium work out just fine, no big deal. In most cases, however, because we don't really talk too much about metals covalent bonding, but for other cases, what we're usually going to see is that these are the genesis of pi bonds. And so with two potential pi bonds, you have the possibility of either multiple double bonds, or if both pi bonds go in the same direction, then we have the possibility here of a triple bond. So an example of that would be ethine, otherwise known as acetylene. Looks kind of complex here, and that's one of the difficulties of trying to do a three-dimensional view of a two-dimensional view of a three-dimensional object. But what we get is with sp hybridization, we see that there are two hybrid orbitals and two unhybridized orbitals. Carbon has 4 electrons in total, so they get distributed between the two groups. The two that are hybridized make sigma bonds, 1 sigma bond to a hydrogen, and then 1 sigma bond to each other. The others go on to make pi bonds. Now, if you're having trouble visualizing the two pi bonds, they've tried to color code it so that's a little bit easier to see. I don't know necessarily if it's been done well. But what you have to kind of imagine, if you will, is let's just say, for the sake of argument, that I've got a sigma bond happening right here. So these two orbital groups are touching. Here's my sigma bond. One of the pi bonds in question would be between this p orbital standing straight up and this p orbital being standing straight up. So that's one of the pi bonds. That would make us a double bond. The other one would be for these orbitals that are going directly into that wedges and dashes plane coming in and out of the board. And so the textbook here is trying to show that by rotating it by 45 degrees so that it's kind of going this way instead of straight at you. But I don't know if it's necessarily coming through off the page that way. So you have, again, if we think about it from that standpoint, we have, here is the one set of orbitals that are interacting. So they are the up and down. And then we have a different set interacting from the side to side. So one pi bond going this way, one pi bond going this way. So you take those two pi bonds plus the sigma bond, there's your triple bond. So these are the most common forms of hybridization: sp, sp2, sp3. We see them a lot in a whole bunch of carbon-based chemistry. One of the things that you get to learn to love in organic chemistry is recognizing the different hybridizations and how those molecular shapes ultimately interact with each other to do different kinds of chemical reactions. But pretty much anything that follows the octet rule is going to end up in one of these three states: sp, sp2, sp3. For the rarer circumstances where we have to break the octet rule by going above 8, there are two other hybridization schemes involved. The first is something called sp3d. That comes from, just if we look at the structure here, this is pf4, or excuse me, pf5. Since the steric number here is 5, I need 5 hybrid orbitals. Now the valence subshells only have 4 available. You've got the S and you've got the 3 P's. That's 4 in total. Where does that 5th hybrid orbital come from to make this molecule? I got to pull from where I have it, the D sublevel. And so with this hybridization scheme, I have to pull in a D orbital to get me to 5. That's the main and only reason why we don't see elements in period 2 breaking the octet rule this way. Oxygen can't make 5 bonds because it doesn't have 5 orbitals to draw from in the second energy level. Sulfur and phosphorus do. And even though that 5th orbital is from a considerably higher in energy sublevel, it's still low enough that making the bond actually makes sense energetically. So that's sp3d, 5 hybrid orbitals from that steric number of 5. For 6 hybrid orbitals, for steric number of 6, it's kind of the same thing. I've got my sp3 that gives me 4. To get me to 6, I need to pull 2 out of the D sublevel. So with SF6, steric number of 6, sp3d2 is the hybridization. That's what's going to get me the 6 orbitals necessary. Now, most of the time, you're not going to see a whole lot of pi bonding in these kinds of arrangements. You're just not going to see it. You're much more likely to see signal bonds all the way around. Or in some of those funky ions that we've had you draw, one of those positions or multiple of those positions will have lone pairs in them instead of bonds. But we treat either way the same. Signal bonds or lone pairs always go in the hybrid orbitals, never in something unhybridized. So in summary, hybridization is ultimately related to the number of electron domains. Now, we've had a funny term for the number of electron domains. We've been using it all week. And like I said, this ultimately comes down to steric number. Steric number 2, it's sp hybridized. Steric number 3, it's sp2. Steric number 4, it's sp3. Steric number 5, it's sp3d. Steric number 6, it's sp3d2. All that we are doing in hybridization is just adding a layer of explanation to what we've already done. So I know that this can be very difficult to kind of wrap your brain around because there's a lot of kind of moving parts to hybridization. You got the electrons and they're all moving around, and you got the orbitals that are changing from atomic to hybridized and so on. Simplify it for yourself. If I can draw, then I can determine steric number. If I can determine steric number, then I can determine shape and bond angle and all that other stuff. And hybridization. It's just one more thing on top of all the other things. It's a representation of the same kind of data. We're just taking it that one little extra step further and trying to put some explanation into why this happens and how it happens. All right, that's all for module 8. That's all for today. On your way out, make sure that you hit the stoplight question. You should be able to do all of the remaining assignments out of module 8 over the weekend. But if you do run into some snags or you have some questions, please feel free to contact me. I'll be glad to help you out. Have a great weekend.